Hi students, welcome to my lectures, and today we are going to discuss about the mixing models because we have elaboratively discussed about the residence time distribution analysis, in which we have sufficient information to find out. We have found that time spent by the molecules in the reactor. To design the non-ideal reactor, we need these three informations: kinetics, RTD, and mixing models. And through RTD, we can able to find out the information about time spent by the molecules in this non-ideal reactor. But thing which we don't know is how different fraction of molecules mix with each other. Example, there are molecules which spend time between 0 and T1, and there are spent molecules which time between T4 and T5. But how the interaction between these fraction with this fraction, and A1 with A3, A2 with A4, A5 with A3, that means different combinations of molecules mix. That means before the molecule exit between 0 time and T1, they might have interacted with the other molecules. This is called the mixing effects. Not just the time spent by the molecules is important, and also how the molecules mix with the other time molecules before it exits the reactor between 0 and time T1. That is what the mixing models will take care. RTD will take care about the time. Mixing models will take care about the interaction. Once you have all the three informations with you, then you can able to predict the conversion in the non-ideal reactor. The first very basic models are zero parameter models, which includes segregation and maximum mixedness model. Rest every other model is a kind of mix of segregation and a maximum mixedness model, in the sense every other model kind of the prediction between the prediction suggested by the segregation and prediction suggested by the maximum mixedness model. That means the most basic models are segregation and maximum mixedness model. Rest everything are simple to operate. So if you can able to understand the difference between the segregation and maximum mixedness model, rest of the models are not that much difficult to understand. So let us concentrate on first mixing model, which is segregation model. Okay, before that, let us give a small recap on what we have done. What we have done so far is characterizations of, because for every non-ideal reactors, there is certain properties which can be estimated through the measurements of E of T curve, F of T curve, mean residence times, variance, and skewness. So what we have done is we have taken small example tracer curve data. Through the tracer curve data, how to estimate these different parameters. Okay. Then what we have done is we have applied these characterizations. That means finding out the E of T, F of T curve with respect to ideal models. Because if you know how these curves looks for the ideal reactor, then we have a reference point to judge what kind of non-ideal reactors are. So through the residence time distribution analysis, we have done this particular part. That means comparisons and then diagnostics and troubleshooting. So then we have observed that compared to ideal reactors, how the curves looks for the non-ideal reactors. Based on the difference in the curves for the ideal reactor curve and the non-ideal reactor curve, we can able to that means we have judged what kind of non-ideality that was existing, whether it's a bypassing or it is a channeling. Okay, these kind of non-idealities we have figured. Okay, now the last part, the part to discuss about the mixing models, where we are going to finally predict the conversion by selecting the mixing models. Okay, the first model that comes in picture is called the segregation flow model. What exactly the segregation flow model? Okay, this is called basic picturization of the segregated flow model. Example, this is a non-ideal reactor. Okay, and we already got the information that through the tracer curve experiments we can able to find out a few information about the molecules spending time in the reactor, because based on this different molecules spend a different amount of time. The conversion from these molecules we can able to get. So that means first of all the time information should be known. So time information, we have already figured that there is a regular flow of reactants that is going in the reactor, in which you have injected certain amount of tracer. This tracer molecules will follow the same path followed by the regular molecules. Okay, the blue circles. Okay, then after entering the reactor, it has now a different name is given, and every molecule has got different name. One indicating the molecules which spend time between 0 and T1, which is designated as 1. The molecule which spend time between T1 to T2 is designated as 2. T2 to T3 is designated as 3. T3 to T4 is designated as 4. Higher the number, more is the time that is spent molecule in the reactor. Okay. When you inject the tracer is also follows the same path. Okay, once the molecule comes out of the reactor, there is a detector which detect at what time. That means from 0 to time to T1, how much fraction of molecules comes in the first instant of time, and followed by the rest of the times. Okay, and you can imagine these are the curves we can expect. E of t, that means time information of the molecule spent in the reactor can be judged through the tracer injection. So through tracer injection curve, I got some certain fractions, right? I got some fraction 0 to T1, that is time spent by the molecules between 0 time and T1, time spent by the molecules within time T1 to T2, time spent by the molecules between T2 to T3, and so on. The mixing model, what is the assumption people have taken in the segregation model? It is said that, example, I know the age 1 molecules, that means which spend time between 0 to T1, during its travel in the reactor, it won't interact with other age molecules. That means 1 will not interact with 4 age molecules, 1 will not interact with 2, 2 will not interact with 3, 3 will not interact with 4, okay, 2 will not interact with 4. That means between the time spent, that means 0 and T1 time, these molecules, they don't want to share any information with the other molecules. So that is what the first assumption that has taken in the segregation model, that is no mixing effect. Okay, so that is what the basic model. That means if different age molecules do not mix in the reactor, then how to what is the conversion in this reactor? It is very simple. I know every fraction, that means this particular fraction, I know it's a kind of a batch reactor. The batch reactor, that means this particular fraction of molecules which time spend time between 0 and T1 will have the conversion of a specific batch which is spent time between 0 and T1. That is, you can see the second set of molecules which spend time T1 to T2. That means this is a separate batch. Okay, this is third is the other batch. The set of molecules will have different batch. That means different batch consist of different conversions, because the first one, the age 1 molecule spend little time in the reactor, the conversion in this particular fraction is very less. The conversion spent by this particular fraction of molecules which is having age 4, which is having the more conversion. That means this batch of molecules have the less conversion, this batch of molecules have the more conversion. Then what is the overall conversion? Average of all the 4 different age molecules having different fraction in the reactor. This is the first assumption in the this is the assumption, primary assumption in this segregated flow model. Then how to predict the conversion? Simply averaging out all the 4 fractions. So that is why symbolically it is represented as this particular age molecules have this particular fraction which is A1. The T1 to T2 age molecules have the fraction A2. T2 to T3 have the age molecules fraction A3, and T3 to T4 have the age fraction of molecules which is A4. Okay, if you go through this particular conversion, what is the conversion? The summation of all the fraction molecules in the particular non-ideal reactor. This fraction information comes from the tracer curve experiment data, which is shown in the earlier page. Okay, sigma of Fraction of molecules spent in the reactor at different times multiplied by conversion in the batch reactor. That means this is the fraction multiplied by batch reactor of age 1. This particular fraction multiplied by batch reactor of age 2. This particular fraction multiplied by batch reactor of age 3, and so on. If you summate all, then you get the overall conversion in this particular non-ideal reactor. Okay. Then fraction is nothing but E of t into delta t. That means this particular fraction, how the fraction can be calculated, fraction information you can get if you know the E of t into delta t. Okay, what is the batch reactor information? The conversion from the batch reactor, which is represented by x of t. If you multiply these both, you get the overall conversion, which is sigma of x of t into E of t delta t. In terms of integration, you get the conversion in this non-ideal reactor. By assuming the segregated model, you can predict the conversion from the reactor using this particular equation. So this is kind of whatever is happening in this particular reactor, they have picturized in this kind of fashion. It's not, don't get confused, reactor, this is not a reactor. Whatever happening in this non-ideal reactor is represented in this way. That means there is a certain molecules entering in the reactor. That means this particular reactor, the conversion from this particular reactor is conversion from all the 4 different age molecules. This particular molecules represented by the black color has spent more amount of time in the reactor. So you take certain amount of fraction. This particular set of molecules, the red one is spending next to the black one. The green one next to the red one. This blue one next to that means the blue one has spent less time and the black one has spent more time. Then what is the overall conversion? The combination of all, which is combined here, and predict the conversion from this particular reactor. So this is not a reactor. Whatever happening in this particular non-ideal reactor, this non-ideal reactor could be CSTR, could be PFR, could be packed bed reactor. Any reactor can fit in this particular circle. In this circle, maybe this kind of things are happening. So predicting this particular conversion is represented in this fashion. It is called, some people represent this particular scenario as a late mixing, because everything is mixing at the final moment. Okay. So let us do a small example. Apply this particular segregation model, predict the conversion in a non-ideal reactor. So it will be more easy for you to understand. Okay, let us find out the conversion from a non-ideal reactor using segregated model. There is a CSTR, which is volume is a 5 liters. Okay, this CSTR is behaving non-ideally. That is why this CSTR is a non-ideal reactor. So you cannot use the basic design equation of the CSTR to predict the conversion. Instead, you assume this particular CSTR is behaving non-ideally. Then you have to predict this non-ideal reactor using the segregated model. Okay, what is the volume? Volume is 5 liters. K is equal to 0.1 per minute. That is first order reaction happening. The initial concentration in the non-ideal reactor is 5 mole per liter, and volumetric flow rate is 1 liter per minute. People have done some tracer experiment. That means they have injected some amount of tracer. At the exit, they have measured. So from the tracer experiment data, the concentration of tracer with respect to time is given as follows. Okay. Then you have the tracer experiment data. That means you have the time information of the molecule spending in the reactor. Okay. Through this, apply the segregated model to predict the conversion in this particular reactor. What is the step? Step 1 is find RTD curve. Second is find the conversion in a batch reactor. And 3, use the segregated model to estimate the conversion. Okay. So step 1, let us find out the E curve. The E curve can be calculated by C of t integral 0 to infinite C of t dt. Okay, that means the concentration data is there, time data is there. Using this concentration and time data of the tracer curve experiment, you have to find out the conversion, E of t data. So as I have used only this particular integration formulas, because every time I show this equation, I use this particular 6-point formula because I have 6 points to integrate. So I use this particular formula. Okay. So using that formula, let us find out what is integral 0 to infinite C of t dt is nothing but 0 to 5 minutes, because the time is from 0 to 5. So integration infinite is replaced with 5, integral 0 to 5 C of t dt. Okay, then I got the information about integral into 0 to 5 c of t dt. Then using this function I can calculate the e of t. So c of t I have got that 13.125 gram per liter into minute. So from this e of t data I can calculate e of t data. So time information, concentration information and e of t information, all the three informations I have received. Okay, the first part of the equation, that means you can see this particular data I have received e of t data. Now I have to get x of t data multiplied by e of, what is x of t? Nothing but batch reactor equation, because I have different batches, so different batch reactors equations will come. Then what is the batch reactor equation? Because it is given the conversion in a batch reactor. The conversion in a batch reactor is given by this, any formula you can use, and given it's a first order, so minus Ra equal to Kca equal to Kco into 1 minus x. Therefore first order liquid phase reaction, it is given that the present reaction is liquid phase reaction. Therefore time information you get if you integrate this particular expression by substituting the value of Ra, then you get the information about what is x of t. But t is nothing but 1 by k into ln 1 by 1 minus x of t. What is x of t? If you interchange the terms, that x of t equal to 1 minus 1 by integral e of t, e power kt. So I know e of t information, I know x of t information. Then I have to apply this formula, that is conversion in the non-ideal CSTR using segregated flow model is integral 0 to infinite x of t into e of t dt. I know x of t, I know e of t. If I substitute different times here, that is time equal to 0, 1, 2, 3, 4, 5, I get the different x of t values. Now I have to multiply e of t into x of t, because the function is x of t into e of t. Okay, so now I got the most informations, time information, c of t information, e of t information, x of t information, and x of t into e of t information. Once I get all the information, I have to integrate this this particular now row. Okay, now my f of t function is nothing but x of t into e of t, which I already am having. I apply the integration methods. Finally, I have found out conversion from the segregated model is 0.198. That is, in this reactor, example, the given problem is so, that means if this reactor is behaving non-ideally, then this non-ideal reactor conversion assuming the segregated model is 19.8%. This is how we can able to find out if you have the data, tracer curve data. What happens, there is another example I want to suggest, that example number 2. Find the conversion from a non-ideal reactor whose volume is 5 liters and the given details as below. Estimate the conversion using segregated model. So same non-ideal reactor is given. The initial concentration is 5 mole per liter and volumetric flow rate is 1 liter per minute. It's a given first order reaction. The rate constant for the first order reaction is 0.1 per minute. Given additionally, the E of t, the tracer curve data is not given. Instead, they have given E of t curve data. E of t is nothing but it's a CSTR equation. That means this is a CSTR. If the CSTR is following E of t equal to 1 by tau into e power minus t by tau, then we have to find out using this aggregated model, find the conversion in this particular reactor. That means here the data is not given. Instead, the curve equation is given. So simply you substitute the value of x of t into e of t. E of t is nothing but 1 by tau into e power minus t by tau. The x of t given information 1 minus e power minus k into t, which comes from the earlier example. So once you know the x of t, e of t information, simply integrate this particular expression. You are going to find out the conversion from this because I know what is tau, volume by volumetric flow rate, you can get 1 by tau equal to 0.2 because tau equal to 5. From these particular informations, the conversion from this reactor is 33%. So this is how we can able to solve. If the data is given, you have to use the integration methods, a kind of a numerical integration principles, and here analytical solution is possible because the line equation is given. So you can able to judge the conversion from a reactor using segregated model. And thank you very much. Let us meet with the new model, which is maximum mixedness model.